Alright, hell yeah. So we got material mechanics, and this is the book of gear. Sweet. And this is probably one of the hardest chapters in the hardest section. It's a plane strain, and that means this little chunk of whatever is going to change in length in this direction and this direction. And because of that, we want to know maybe what happens at a diagonal. So this is kind of easing our way into it. It's taking a rectangle, and we're given its change in length in the x and y, but we want to rotate it at some sort of angle and then know its change in length in the x and y. And strain is what that's called, and how to quantify it is it's going to be a change in length divided by the initial length. And so that's the first thing I'm going to go over, because, man, you know what I mean? They're going to use the term delta, and that's going to be for a change in length, or you can just use change in length. So it's good to have a couple different ways to write the shear equation. This is just the general definition for normal shear. So it's going to be, you know what I mean, I have an object, and it's going to get bigger this way or this way. And those are going to be the normal directions. This problem is just going to have stresses in those directions, and it's not going to have any shear stresses that are going to cause you know what I mean, two parts of whatever this is to move across each other like that. So we're not going to get any change in angle to form. We're not going to get that going on. So that kind of makes it simple just for our first go around. So hell yeah. So we can see that this is strain is just change in length divided by the initial length. And we have an equation with three things. I always teach, hey, rewrite this three different ways. We only really need to rewrite it one other way. We just need to know, we need to solve for the change in length quite often. And so hell yeah, so change in length is just get this, which was downstairs, up here. So the strain times the initial length is going to be the change in length. And we're going to be, for these problems, we're going to know the strain in the x direction and the strain in the y direction. And those things are going to happen simultaneously. This thing's going to, you know what I mean, get, as these loads are being applied. I mean, you could apply one load at a time. You could apply a load this way, and then you could apply a load that way. So, cool. The other aspect of this video is to use the calculator and potentially less pen. Sometimes I get really injured wrists if I just really go to town. And it's also good to find other ways to, you know, I definitely really like writing the algebra because it, you know, I can find my mistakes, I can make mistakes, I can see my work as we go. And just thinking through a problem, it seems like it doesn't stick. But this will give us just a little bit, a better chance of it sticking, just kind of using our calculator. Okay, so this, what is it? Is it a chunk of metal? Well, you know, I mean, you can kind of tell maybe what it is. Well, I guess not. I mean, it could be a chunk of rubber, and whatever, you're just putting a load on it, which is causing a force over an area, which causes stress and PSI, and that's going to cause this thing to change in length. Now, it does have dimensions. It is 8 inches by 4 inches, and the strains are very small. You know, I mean, we have 195 times 10 to the negative 6. I guess we can write like one or two things just to show you that this number is 195, but it's 10 to the negative 6. So we're going to go 1, 2, 3, 4, 5, 6, put the decimal place, and then fill in these little cradles with 0. So this is the number. So I would get used to writing these as, like, in your calculator, I'm going to do this as negative 0.1230 and 125. And I can get there fast just by saying, hey, 123 is 0.125 times 10 to the negative 3. And then we're going to go 3 more to get those 3 zeros right there. So hell yeah. And booyah. So that's the first thing that I'm going to do. I'm going to start plugging the dimensions in. So 8 stored as alpha b. And a commenter was like, hey, can you go over kind of how you use your calculator? Well, it's hell yeah to store these variables. You know what I mean? Because then Because then, if I know I'm using the numbers, but then I'm actually calling it a variable in my calculator, and the equations are going to be in terms of variables, it just helps you kind of understand that these equations, your inputs can change, and I don't know. So maybe enough said. So we have 4 stored as alpha h, and booyah. So we got alpha b, alpha h. You can always just double check. It's going to be the biggest error you're going to come up with. You're going to store values into your calculator as letters, and you might start overlapping, and then your answer is just wrong. You're not going to know why. All right, so 2 ways to insert this. We can do 195 times 10 to the negative 6. Cool. Or I can just do 0.123, 195. You know what I mean? How many sweeps? Look at this. 1, 2, 3, 4, 5, 6, 7, 8. That took 8 characters. Well, this took 1, 2, 3, 4, 5, 6, 7. Hell yeah. So even just doing this, and the decimal equivalent is probably going to be better for your understanding of what this number is. And then also kind of converting back and forth. Because in the end, we're probably going to get an answer, like our change in lengths. And we'll have to explore that in a moment. But hell yeah. All right, so that's going to be stored. I'm just going to store it as x. So x is going to be my strain in the x direction. For this, I'm going to have negative 0.1230 and a 125. Store that as alpha y. And we'll double check that negative 125 times 10 to the negative 6 is that same value. Okay, sweet. So I have every parameter in my calculator. Now let's ask what it's asking. So this thing is going to get changed in length in this direction and this direction. Now this is going to be a negative, so it's good to just kind of visualize. This one's going to lengthen this way, and then it's going to decrease in length this way. Now if this thing was a square, it would, because the strain is only proportional to the length. And so we know that the change in length is this 195, and this is a very good time to just think of this as a quantity of 195. I mean, that's why they do this, because small numbers are humans do not like small numbers. But in general, we're just comparing this 195 to a 125. You know, we know that this is negative, that means something. But yeah, 195 to 125. Now this 195 is associated with a larger initial length. So we know that if we have a strain in this x direction, that's the strain in the x direction, the change in length will be the strain times the initial length. Cool. So we're going to have, I don't know, and let's just try to do some guesstimation. Let's say this is 200, and then 2 times 8. 2 times 8 is 16. And so we're going to have 16 with 3 zeros. Okay, so we're going to have 16,000, you know what I mean? Minus whatever that's going on. I'm just trying to get a value for this change in length. So let's just say 16,000 whatevers. Now in the y, we're going to have the strain in the y is negative 125, and then our initial length is 4 inches. And so cool. We're gonna let's double this first to 250. Double it again, so we got 500. All right, so we're going to be going down 500. Our change in length is going to be 500 this direction and 1600 this direction. So that kind of gives you the proportion. Now it is good to be like, well, I mean, we should know exactly how much this is going to change in length. So let's do that. So the change in length in the x direction, and it is good to put subscripts on these. So it's the strain in the x direction is the initial length in the x direction. So now we can find the change in length in that x direction. That's going to be 195 times 10 to the negative 6, or it's going to be 0.123195. Hell yeah. Times the initial length of 8. All right, so we got this. I mean, we just said that this was going to be pretty close to 2. Like, you know what I mean, like 200 for that, and then and now let's just multiply by 8. We're gonna get and you could think of this as just 16, but now we have to move Like this is 2. So if we go 1, 2, 3, 4, this is 10 to the negative 4. And so this is my way of multiplying exponents. Is like, hell, I know this is a 10 to the negative 4. And this number out here is a 2. This number out here is an 8. This is 10 to the 0. Okay, so I'm going to go 2 times 8 is 16. And now I'm going to go 10 to the negative 4. Or I can go 16 and go 1, 2, 3, 4. And just get this as a 0.0016 inches. So that is how much this is changing in length. And this is going to happen, because if this is made of steel, even if you're loading it almost to like its failure point, you know what I mean, the change in length might be imperceptible. You know what I mean? Because an eighth of an inch is 0.125. A 16th of an inch is, and I'd say that's pretty close. You know what I mean? Let's say this is fairly close to 0.16. And so that's going to be an eighth of an inch. So what would we have to do? You know what I mean? If that's 0.16, we would have to go chop an eighth of an inch. Yeah, and an eighth of an inch is perceptible. You know what I mean? That could be an eighth of an inch. We would have to chop this thing up 100 times. Okay? So we chopped it up 100 times, and then one little dash of that is going to be the change in length in that direction. So even just what I did right there is tip-top when it comes to actually understanding and just making sure you have an idea of what's going on. I mean, you can't just say 10 to the negative 4 and compare it to 10 to the negative 5, and then, you know, and 10 to the negative 3 is just like without actually having something, you know, to gauge it by. And even that's a pretty crap gauge. You know, what's a hundredth of an eighth of an inch? All you're saying there is, well, that's pretty small. You know what I mean? Alright, hell yeah. So machinists work in thousandths, which is only this. You know what I mean? Thousandths, but some work in tens of thousandths. So, you know, the tolerance at a very, very high, like super high level. Holy Toledo. Even dial gauges on like horrible, you know, Harbor Freight stuff is just going to be, you know, 0.01 or worse. But hell yeah, but some of this stuff can get intolerances of down to 10,000. And so what number did we pull? Hey, we pulled 1.6 thou. You know what I mean? So hell yeah, that's going to be, so we're more than 1,000th of an inch. And hell yeah. And this one's pretty cool, because if you take 2 stacks of playing cards and put them together, hey, you get about 1 inch. And there's about 50 in both decks, so you get about 100 cards. And that's going to be 100 cards per inch. So each of these is going to be 10 thous of, you know what I mean? So each card is 10 thousandths. So if you had a playing card, a tenth of that is going to be the change in length in that direction. So I don't know. You know, I'm glad I spent about 5 minutes on that, because that's the criminal part about material mechanics, is the idea of getting used to very small numbers, and you have to associate them with very big numbers, and that's also crazy. But the main goal of material mechanics is saying that, hey, this material can only withstand a change in length of that value per the initial length. You know, change in length can only be so big a number if I know the initial length. And that ratio is going to be the same for all steel. And so that's why this ratio doesn't change, and we call it strain. So strain of steel can be 0.002. It's a really good one to bring up like all the time, because we have 1 meter or 1,000 millimeters. We can lengthen steel by 2 millimeters. Hey, that's fairly perceptible. And that's when it's going to Play-Doh or, you know, yield. And in certain situations, hell yeah, you might say that's gonna fail. Your yield might induce failure. So, booyah. And then so we know material mechanics is like, hey, we know if I know the value of the strain, take a step back. This whole section is because we actually have electronic devices that have thin wires, and they're going to be in this pattern. And when all we have to do is like literally glue it to the bridge, And then, well, yeah, that's interesting, because you would have to glue it on prior to being fabricated if you wanted to know the pre-stress. Oh, that's fascinating. I'll have to research that. But let's say your bridge is fairly lightweight and strong, and then you throw a bunch of cars on it. Now this thing is loaded, and so when the bridge kind of does its thing, stretches in all directions, these wires are going to thin out, and the electrical current running through there, it can measure that resistance. The resistance in the wire is proportional to that change in diameter, and that change in diameter due to Poisson's ratio gives you the change in length in this direction. So it's kind of fascinating. You know what I mean? The change in lengths in the diameter direction is proportional to the change in length in the direction we actually want. Sweet. Alright, so I guess we got a little idea of why we're getting values and what we're going to use them for. Alright, hell yeah. I kind of wanted to put the pen down though. So, booyah. So there's two different ways to go about this one, and well, there's actually many ways, but let's see what they want. So it says, determine the following quantities. Oh, bummer. And we should have a line right here. It had a picture on the other page, and it said this angle was, I'll call it by its right. You know, I watched a YouTube. They said this is phi. Just like pi is pi, this is phi, not phi, or whatever. I guess I can get used to that. And hopefully I got this right in the book, but this is going to be, what is this one? You know what I mean? That's in quantum physics. Makes you feel like you're doing quantum physics, but it's just a Greek letter, so that's going to be that angle right there. Yeah, phi, is this psi? I have no idea. Alright. But anyway, so we have these two angles, and you can just get these by trigonometry. We know this is 8, this height is 4 inches, and this is 8. So that's going to be our first equation we're going to use, is that this angle is associated with the two things. So if we do have a right triangle, you know, kind of my moniker is like, if you know two things about a right triangle, you know everything about it. And so we know two sides of this right triangle. Hell yeah. That means we know everything about this right triangle. And so, and you know what I mean? I mean, we can use all the equations, the 8th grade equations of SOHCAHTOA or whatever, to find everything we want to know about this right triangle. What we want to know is the angle. And so we see that this angle is, I always do like some sun shining rays. So it's shining on this opposite, and that's going to be associated with the sine. If we knew this hypotenuse, hell yeah, the sine of this angle would be 4 divided by the hypotenuse. Cool. And then this would be the adjacent. So if we knew this hypotenuse, the cosine of this angle would be 8 divided by the hypotenuse. Alright, and I guess that is literally the definition of what tangent is, because I just have two equations with theta in them, or whatever phi is. I just said that sine of 4 divided by the hypotenuse. Let's do this one. I mean, because I just second-guessed the fact that I know tangent. But hell yeah. So I have one equation. That's sine phi is equal to 4 divided by the hypotenuse. And my second equation is cosine phi is 8 divided by the hypotenuse. Two equations. Check it out. Two unknowns. I'm going to solve one for I'm going to solve this for h. Get h upstairs. The sign goes downstairs. So hell yeah. So h is 4 divided by sine phi. I'm going to shove that in right here. So we're going to have 8 divided by 4 divided by sine phi. So hell yeah. So we have 8 divided by 4, and then the sine phi goes upstairs. What we really want to know is what phi is. So we have a cosine phi and a sine phi over here. We're going to get the cosine underneath the sine. And we're going to get this to the other side. So we have 4 divided by 8. And then we're going to have sine phi divided by cosine phi. Hell yeah. And we know this is tangent. Tangent phi. That is, you don't have to call this tangent at all. You You know, and that's a good thing. That's a good skill to not do. Don't call this tangent. Call it sine theta divided by cosine theta. So hell yeah. And I'm just going to kind of flip and do 2 steps at once. But if we want to know phi, we got to take the inverse tangent. I guess you can just do it of both sides. I never do that. I just say phi is the inverse tangent of the opposite over adjacent. But hell yeah. So theta, phi, sorry, this angle, this initial angle is going to be inverse tangent of 4 divided by 8. And that's kind of what we have. Inverse tangent is this opposite divided by the adjacent. So sweet. So we have that little equation right there. And kind of nice little proof. And so we're going to throw that into our calculator. Alright, booyah. So we have inverse tangent of 4 divided by 8. I'm going to put this in my calculator as theta. Alright, so, I mean, we could just, at any point we could plug and chug if we knew what we were doing. You know what I mean? If we knew how to use the transformation equation, you know, because one of the things that says, what's the change in length of this diagonal? You know what I mean? And this is going to be the x, strain in the x prime. This dimension is x prime, and 90 to it, this is y prime. So this is the x-axis, y-axis. We rotated it up this angle. This is going to be the x prime, y prime. This is the equation that we prove. You know, I've made like now 4 videos, but I haven't done like you know what I mean, bee's knees all the way through. We're going to try to do that and try to get as shorter as possible. You know, more crispy. But hell yeah. So but again, this is going to be strain. Still, we need to go back to like, what is strain again? Strain is change in length divided by the initial length. All right, cool. So let's just write that down. So strain in this diagonal x prime direction is going to be the change in length in that x prime direction times the initial length in that x prime. So this is a good thing to get used to in material mechanics, is just kind of putting subscripts and kind of talking your way through that. That's kind of what we're doing. And yeah, enough said. Cool. So and this strain in this direction due to this equation is, the whole idea of this equation is that, hey, that device that measures, what this device does in all these problems in general is we know the strain in the x, the strain in the y, and then like the rotation, which is this angle that forms, which number-wise is very similar. It can be either similar or sometimes double. Well, yeah, it can be similar or double, but it's going to be the strain in the xy. Because when we do strain, to compare it with the Mohr circle, we actually divide this by 2. So that shows you, so I will write this one down, that with steel, strain of steel is 0.002. But that's the fact that I have an initial length. And that's going to be the change in length, 2 millimeters divided by the initial length. So that's where that comes from. So strain is change in length divided by the initial length, 2 divided by 1,000, got it? Where the change in angle is definitely something different. If I have this to be 1,000 millimeters and this to be 1,000 millimeters, what's happening is this angle's changing. These angles are so small that you do get an arc to form, but we're just going to say this straight line is that. And so this is the angle that forms. And then even, I mean, it really should be half angle there in a diamond, where both of these angles add up to that. So this is, you know what I mean, that's going on. But anyway, so you have an angle that forms. And we need to use the equation that radians times radius is arc length. You know, this is an angle in radians, that's an angle in radians. This is the radius here. So we can just do this. We can do radians times 1,000 is going to be the arc length. And the arc length that forms when we do this is going to be 4 millimeters. So when you shear something, steel can move 4 mil. If you got 1,000, if you got a radius of 1,000, it can shift 4 millimeters and change that angle. So that's kind of interesting. And that means that this angle in radians is 4 divided by 1,000. Because if we rearrange this equation, the angle in radians is the arc length divided by the radius. Well, arc length and radius are both in meters. But just because the angle is small, and what we're doing here is just like, well, wouldn't this drop down if you're saying this is you're saying that this is your hypotenuse, your radius, and so if this was your hypotenuse, you would have to drop down a right triangle, and if you were trying to find this distance, you know what I mean? So you got 3 things going on. We're saying this is one is that you're going to have an arc. 2 is that we're just going to say it's a straight line across. And 3, if I'm calling this the radius, and it's going to have this angle, dropping down, this would be the hypotenuse, and this would be the components of that right triangle. So this is where the approximation is. And, I haven't even made videos on how to really technically show that difference in approximate. I think that would be very useful instead of just kind of sweeping it under the rug. And, because even right here, this is still not the arc length, but it's going to be, if I'm saying this is the hypotenuse, and this is a component, the sine component of the right triangle, then it's going to be r sine of the angle. So we have r sine of this angle in radians is going to equal, basically the arc length. And so we're going to say the arc length. And so, but when we're dealing with radians, sine phi is just approximately, sine of the angle is just approximately the angle. This term is gamma. Sorry about that. Is that gamma? Hell yeah. So that's where you just get this as an approximation, and you get r radians arc length. Radius times radians is arc length, but I for sure like to say it radians times radius, because radians is bizarre, and if you multiply it by the radius, you get something normal, and that something normal is arc length. Alright, let's move on. But hell yeah, I never mind going over the radians times radius is arc length, because it can stir you, because it's a small angle approximation, and it seems like an equation that comes out of nowhere, and it has bizarre symbols where you have an angle, a radius, and an arc length as s. S doesn't get used as much as, there's probably very few problems even in high school that you use arc length. But that's one that you should be using on a daily almost. All right. So hell yeah. So you get this. We did that just to show that you're going to get 0.004 radians. Different units. This is meters per meter. That's going to be change in length in units of meters divided by initial length and in units of meters. That's what's going on here. This is radians, which I guess, if you're getting this, that's going to be radians, which is, and it's a linear approximation, so you can't just say it's arc length in meters divided by radius in meters, because, yeah. So anyway, so it's just kind of one to be like, all right, we know what we're talking about. If the angle in radians is small, and I have that, I can multiply by the radius to get the arc length. If I had the arc length, I could divide by the radians to get the radius. So still you got an equation with 3 things. You can rearrange it 3 different ways. All right, so I just showed you there. That is very important. It shows you there that this angle that forms is different, way different than just shifting in the normal shear. So this angle that forms, that's called shear strain. Strain is just a word for deformation. I just like to think changes in length. But obviously, normal strain is a very obvious change in length in the x or the y. Where shear strain, I don't know, nothing really has to definitely change in length per se, but no, this length changes. For sure from there to there, this length gets longer, this length gets shorter. And so you can still think of it as a change in length as well. But it's measured in the angle change. I'm just showing that that angle change is only twice. This max angle change, which is called shear strain, and shear strain is this angle that forms, is going to be just doubly proportional to the max normal strain for steel in the x and y directions, just the normal directions. And that's just good to know, you know what I mean? So when you're doing problems and you're trying to hit values and you're trying to double check your answers, hey, you can maybe expect that this might be a little bit doubled than those terms. And just at the max, I mean, your max values. I mean, because what we're going to see is these can be, you might not have any of that. And for this problem, we don't. We don't have any shear. Even when we rotate the element up, like we didn't have any of this to begin with, and so when we rotate the element, we don't have any of that as well. Alright, so, booyah. Alright, so what do we want to do? So the increase in change in length of this, what did we spend our time doing? Well, let's in our calculator calculate those change in lengths again. So our x value is the strain, and our initial, so we're going to multiply that by 8. So strain times initial length is change in length. Okay, so now I know this is the change in length in the x. I'm going to store that as alpha a. That's the bummer. I just kind of made a video on pros and cons of this video. It would be nice to also have x1, x2, you know, just store values up to x99, because then you would just have to go, you know what I mean, 8 stored as alpha x1, you know what I mean, that's all you need to do, and then it would store it with a subscript 1. The technology of the TI calculators are dinosaurs, so I'll definitely call that out. You know, they really haven't changed, and their patent's up. Anyone could just really just copy, you know what I mean? I mean, because there are just some useful aspects of just, I like the buttons, I've just used this for my entire life, but it's just, you're not going to invoke change. How are you going to change this thing? So anyway, so that was the change in length in this direction. And so for these problems, it's very important to get fast at understanding this change in length is the strain in that direction, the normal strain in that direction times the initial length. So if I want to know how much this is increasing in length this way due to a positive strain in the y direction. We don't have a positive, but still, we can still treat it like a, the change in length will be the strain in the y times the initial length. And that's going to come out a negative number. And that's going to say that, hey, this length didn't go that way, it actually went this way. All right, let's do it. So we have that alpha y, and we're going to multiply by that height 4. All right, I'm going to store that as just alpha b. Cool. So now we know our change in lengths. Now maybe we want to know our final lengths. Because if this thing is going to go this way and then go this way, so that's literally what's going to happen. This diagonal line is going to be right there. So one way to do this problem is just to find the length of this diagonal line and subtract it from the length of the original diagonal line. You know what I mean? Not too bad. And so the initial length of this line was just Pythagorean's theorem. So it's going to be the square root of 4 squared plus 8 squared. You know what I mean? This squared plus this squared is the hypotenuse squared. I want to know just the hypotenuse. So let's take the square root of 8 squared plus 4 squared. So we got the square root of 8 squared plus 4 squared. And I'm going to store that as alpha d. And then using the letters on my calculator, I'm going to store this new hypotenuse as alpha e once I get there. And so I found the change in length in this direction. That's all I did. I found that change in length. So what would be the total length? Well, it's going to be 8 plus alpha a. And so now this is my total length in that direction. We got to store it as alpha. And I like to pick common letters, you know what I mean? So maybe G and H. So we're going to go alpha G for this length right there. And maybe I can just kind of put that right here. And then this total length I'm going to put as alpha H. There we go. Alright, so this total length h is going to be the change in length. That was going to be b. And then plus 4. So we have 4 minus, basically that change in length was a negative, so we get a little bit less than 4. I'm going to store that as alpha h. Alright, so now I can just find this hypotenuse. It's going to be square root of g squared plus h squared. Alright, hell yeah. So let's do that. Let's do the square root of g squared plus h squared. And I'm going to store that as e. You know what I mean? Because in my calculator, I only have 26 letters. That is seriously the bummer. These should be lowercase and uppercase, and then Greek. That would give you 3 times as many letters. But I guess I just made that video, and I'm kind of, I don't know. It's just like, how do you, like, yeah, maybe I can ask my brother and be like, hey, could I actually program? Is there a calculator that I can change the actual inputs of the keys? I mean, because I need a project. If I'm going to learn like computer programming, you need a project. Well, that would be too complicated, but you actually need some motivation. You need to be like, hey, computer programming would help me solve a problem and make my life easier or fun. Like, that's the gaming world. So that's why I'm going to do it. But I haven't, you know, I don't know what that door looks like. And but anyway. Alright, so hell yeah. So we stored that diagonal as alpha e. Now the change in length is just alpha e minus alpha d. And everything is just, you know, crispy. And so I'm going to say that's going to be alpha f. And so we have our first value. So change in length in that x prime direction is stored as alpha f is 0.00117. Usually you just need, and that's going to be in inches. Alright, so now we're going to show you that the length final, all we did here was do the initial length and then 1 plus e. And so, so let's FOIL this through, because that's going to be the initial length plus the initial length times the shear strain. Dang it, I always mix up these. Normal strain in that x direction. And let's write this one more different way. So strain times initial length. And that's going to be length final. Because all we did was take the length final, square it, this length final, square it, add those two together, take the square root. That was the length of this hypotenuse. If we wanted just one equation to do that, we can see that this length final was that 8. I mean, the first thing we did was multiply this 8 times the strain in that x direction. We went 8x, and then we stored that as alpha a. You know what I mean? And then we added it to 8. You know, because we found the change in length and added it to 8. And so that's the same thing as taking 8 multiplied by 1 plus the strain. You get the same number. So it's things like that like if you just did this for your first go, you'd be like, nah, that's too confusing. Like for me, that was too confusing. It's like, nah, no thanks. I don't see where the algebra is really kicking in. But yeah, it's good to see those. I think those are like the light bulb moments, but they're still kind of tricky. Like especially with trigonometry. You know what I mean? To see that if you have a sine theta, cosine theta, you're just like, oh, hell yeah, that's 1/2 sine 2 theta. You know what I mean? Just all your... And it's not that I have memorized that. You know what I mean? I've actually gone through... Every time I go through the actual graphical proof, and that's the only reason that sticks. Same thing here. The only way you're going to see that this is going to stick is to like FOIL it and be like, oh yeah, that's exactly what I did. So people want to know like how I tackle, like how do I learn what's going on, especially with technical material. Like if I think the proofs are too hard to even read through, because any subjects like that, it's so fascinating that still at the end of the day, like all college is equations and answers, typically with algebra, because algebra is a continuation, you know what I mean, to be like inputs to outputs, and you have this continuous, you know what I mean, that's why it's like not quantum, but it makes college doable, Like, and you know what I mean? There's answers in the back of the book. You literally just use multiplication and division to get those answers. And so that is the first way that I approach things. Even though it's like, I mean, because you still are playing around with it. No, that is I'm going to double down and saying that is a very good method. Because what you're doing is you're seeing what numbers are getting multiplied. If I have 2 apples, and then I consistently see that I can make 1 pie out of 2. Alright, hell yeah, we've got some more juice. But I guess where I'm going with that is if it's really powerful. If you can see what numbers are getting multiplied together, well, those numbers are probably always going to get multiplied together in that order. And sure, there was a reason they did. And that is why even taking a problem from like the inputs and then just starting to, especially if you can put it together, like what we're doing here is just using trigonometry and showing that, where some of the equations, like even this, the identities get put in and then it looks something totally different, and then you kind of lose all idea of where an equation came from. And so hell yeah. So we found it once, and this is a good time to show. I did draw a. All right, hell yeah. So this is the proof of a rotated element. And so even though I've already done this a bunch of times, it's like how can you look at this equation and be like, oh, I know why this is happening. And so we have a cosine squared, and I've made videos on this. It's just like, well, let's say you just had one cosine. I just had EX cosine theta. Well, I teach that cosines are going to be percentages. You know what I mean? So you're kind of taking a percentage of that strain in the x, okay, which is usually a smaller number. Well, okay, cool. What if I took a percentage of a percentage? Okay, it sounds like you're going to take now a proportionally smaller number. You know what I mean? Same thing over here. You got a percentage of strain in the y, and then you got multiplied by another percentage. And so that's what's going to take place here. The proofs, and I do a better job than the actual textbooks, because we're going to start with a dx, dy element. So this is the dy, this is the dx. This element right here is the same as the element right here. We're going to rotate this up an angle theta, and we want to know like how much it's going to strain in that direction. That's all this equation is. Strain in this new x prime direction, x1 direction. And so if I knew the change in length up here compared to the initial length, that would give me the strain in that x direction. If I knew the change in length of this line compared to its initial length. So we're still using the fact that strain in the x prime direction is just the change in length divided by the initial length. Initial length for this is dx. We don't know that, but we are given our inputs, strain in the x, strain in the y, and then that shear. For our problem, we don't have any of that, so it keeps it simple. So now we have to box this in. And I know if I just draw an imaginary box that encapsulates this diagonal, well, I know this is still going to strain in the x. And then I know that if this imaginary box changes in length in that x, that this diagonal has to still be at that corner. And so, hell yeah. So we can see that it lengthened. When this strains in the y, okay, that diagonal still has to be at that corner. And they'll say that for these proofs, you know what I mean? Like, these changes in lengths you can superimpose them. So we can do one first and measure this change in length. So this change in length in the x is the strain in the x direction, given strain, multiplied by the initial length. So our initial length is dx cosine theta. And nothing too tricky there. We just took our dx, dy, rotated it up. I really am interested in the change in length of this dx, but I need a square, so I kind of box it in. If this hypotenuse is dx, then this is just dx sine theta, dx cosine theta. So it keeps it real basic, no bizarre trigonometry or just uncommon, trig proportions. And so now this is that length of that imaginary box. I know it's going to strain, and I know its change in length is strain in that direction times the initial length. So hell yeah, this change in length is strain in the x, dx cosine theta. And that's going to be this line. This whole imaginary box is going to shift that much. So I'm going to come up here to this point, draw this. This is going to be my hypotenuse. This isn't the, this could be pretty close to what it changed in length, but we're going to say this is hypotenuse, draw our rotated coordinates, and now we have a right triangle. This is theta, and so the change in length right here is going to be a cosine component. So we know our hypotenuse is strain in the x dx cosine theta. We want to take a percentage of that because it's a hypotenuse. What do you call these? If this is the hypotenuse, these are going to be smaller. Your sides of a right triangle are going to be smaller than the hypotenuse, proportionally, and percent-wise. And it's going to be, and hell yeah, this is the angle. Sun is shining. This is the sine component. This is the cosine component. So we're going to have cosine theta. So we're going to take that hypotenuse and then cosine theta. So hell yeah. And you're going to do the same thing in the y. This is going to be my hypotenuse. This is going to be my angle theta. That's kind of the trickiness, is just like, figuring out which angles are which. But this is theta, and we're interested in this change in length. That's going to be the sine. So this is going to be strain in the y times the initial length, dx sine theta. And then we're going to have the sine component. So hell yeah, that's going to be strain in the y dx sine squared theta. That's going to be we just found the change in length. And divided by the initial length dx, dx's cancel. And you got ex cosine squared, ey sine squared. And that's this equation. You know what I mean? And we just don't have any shear for this problem. So booyah. Alright, hell yeah. So I guess I'm doing quite a bit of explaining. Like you could just, just plug it in. So now at this point, we might as well just plug it into this equation. So we have our angle theta. We already came up with that one. That was inverse tangent of 4 divided by 8. We can just double check. And our strain in the x and our strain in the y. And that's it. We're just going to plug it into this. So we have x cosine theta squared. Whoa. Alright, and then we have plus our strain in the y, sine theta squared. And then booyah. And then so here's our strain. I'm going to multiply by 10 to the 6, or this is 1.31 times 10 to the negative 4. Just move the decimal place this direction twice, and that's going to be 131 times 10 to the negative 6. Or just multiply by 10 to the negative 6, and we got 131. So there you go. So our strain in the x1 direction is going to be this value. So I'm going to store that as m. So that strain is m. Now, part A said we want to know the change in length. We just found the strain in the x1 direction. And we need to know the initial length in the x1 or x prime direction, and that'll give us the change in length. So we found the strain. That's going to be m in our calculator. The initial length, well, that was just alpha d in our calculator. So hell yeah. So d times m, and that should do it. Whoa. M. Oh, sorry. So this got a little bit. So this strain was times 10 to the negative 6. I just multiplied by 10 to the 6 to show you that when dealing with strain, I mean, you're going to be kind of in this ballpark of hundreds or thousands. Because 0.002 for steel is move the decimal place 6 times. 1, 2, 3, 4, 5, 6. That's going to be a value of 2,000. So your strain values are going to be in between like 50, 20, like 10, 20 to 2,000. You know what I mean? They can be 0. But they're probably, for metals, they're probably not going to be more than 2,000, which would be 2,000 times 10 to the negative 6. Because if I have 2,000, 1, 2, 3, 4, 5, 6, there you go. That's going to be 0.002. 2,000 times 10 to the negative 6 is 0.002. Alright, so this was the value for strain M, and now M times D gives us that change in length that we were looking for. Now check this out. I got to store this as alpha. I'll store it as alpha K. So alpha F was using geometry. That was actually 100% accurate. This involves small angles. We just said that. Actually, I did not say that this involves small angles. If this changes over here, if we want to find the true change in length, so if I drop this down to there, let's say, let's see. So this angle alpha happens. So this angle is going to be theta minus alpha. So the complementary angle up here is going to be 90 minus theta minus alpha. Okay? And so that's going to be this angle. This is going to be a 90 degree. So this one, and so this angle is going to be complementary to that. So this angle right here has to be theta minus alpha. One way that I teach complementary angles is like, hell yeah, one's going to be theta. One's going to be, let's say, theta. That's the one that I usually like to use for my primary angle. And then I just say the other one's phi. If the angles get real small, especially with these proofs, I just do this. I say that is theta, and a dot is the complementary to that. So then if I have a 90 degree corner, hell yeah, I know that this is theta. 90 degree corner, I know that that is phi. And then here's my 90s. Okay, so if I was trying to, I'm going to take a quick pause just see if, because I've never done this, you know what I mean, to make sure to see what's 100% accurate. Now we got this. So this line for sure can just get extended down, right? And then because this diagonal moved to this point, it's now right here. And now this is the diagonal line. And so this angle is alpha minus theta. I'm just going to say this is the complementary. This is the strain in that direction. So this is a horizontal change in length. And what we're really interested in is this component right here. If this is the complementary associated with phi, then this angle has to be that theta plus 90. So I'm right. So this is going to be theta minus 90. Sorry about that. And I know my hypotenuse. My hypotenuse still for sure is 100% EX, you know what I mean? The strain in the X times the initial length, dx cosine theta. But I just want this cosine component. So the strain in the, the change in length in the X prime direction due to the strain in the X. You know what I mean? Because it's kind of like, and then you're going to add them. See, what we're just trying to solve for is this one just more accurately. That's going to be EX dx cosine theta. You're still going to have this cosine theta. That's still the initial length. But then when this changes in length to there, this component is going to be cosine theta minus alpha. Hell yeah. And then even to find this alpha angle, what we do is we just say, hey, this arc length right there, we're just going to call it S. It's not even an arc length. It's literally, you're doing this. You're saying this angle is real small, but check that out. That straight line is the same thing as an arc length. And, yeah. And what you're saying is that these radiuses are the same. You know what I mean? So that's kind of the approximation, which gets you, yeah. So that's, and that equation is radians times radius is arc length. And so I know this arc length, and I could know it in terms of just the not using the small angle, because that's just going to be EX dx cosine theta, and then times sine theta. So let's do this one. So alpha. So radians times radius. So we have alpha dx. That's radians times radius is arc length. That arc length is going to be this hypotenuse. That's going to be EX dx cosine theta. And then we're going to have the sine component of it. And cool. And we just said that if this, yeah, it's so bizarre. Like that's what makes my mind melt. Is like, okay, we did a small angle approximation, but I kind of really want to know how to solve for it truly accurately. Because for this, I'm still gonna, even if I throw in the angle does change, and what are we gonna do? We're going to say that, no, yeah, let's see. So even if this angle changes, this is my hypotenuse. I'll have to look at this one again too. Alright, so I need to back up because I ran into an error when I solved for this. This is wrong. This doesn't necessarily get you any closer to an answer. And the reason is because this length dx, when this shifts over, like this length dx would only maybe go to there. You know, like this would be the radius, this would be arc length. And so that little gap right there, I'm picking up error. Because yeah, sure, I can have this as my length, I can know that definitively, and I can say that this is theta minus alpha. Cool. But that's only going to give me this component when I take the cosine component. And so that change in length has a little bit extra. So this is going to be undershot. And so, if we're trying to get more precise, there's no reason to not get 100% precise. So that is going to be for another day. To be like, hey, I really do want to figure out what the actual... and then in one of my videos, I said that because of this approximation, it wasn't very good. No, it was just that I was making an error. I thought it was, you know what I mean? When I get this change in length of 0.00117, I thought this digit was like 2 off or something. Hell no. So we're going to show that this number accurately was 0.001171779. And with this, even though it comes from an approximation, and sorry I spent so long trying to show you something that was 100%, but no, this is not 100% either. So there's no reason to do that. That'll be for another video. But we did do it with the approximation, and that value was going to be 0.00011716. So there's the difference. And then in engineering, keep that in mind, because 3-digit accuracy is kind of what you're shooting for, and we basically have 4-digit accuracy, and then it deviates. So these small angles are for sure. So what I said in a previous video is probably deep as into it, so it doesn't really matter. But that was a wrong statement. And so kind of brings up the idea of, hell yeah, again, making videos, you know what I mean, putting yourself out there, because if you do, if you solidify it and push the publish button, that day or the next day, you're just so much more likely to have things click, just because it is no one wants to put wrong information out there. Don't get me wrong on that, but all right. And so we can even show the error, and again, like why was this accurate? Because we said we know the strain in this direction, we know how much it changes in length, and we know that it squashes in this Y. So the final shape is looking like this. And we know this line, this diagonal is connected to there. So, and we know the initial length by geometry, 100%. We know the final length, 100%. So that's what we did, and we got that. So that's 100%. This is a little bit less, so we're going to go alpha f minus alpha k. So we're going to take the 100% change in length value that we know, f, minus the one that we thought was a little bit off due to the small angles. So we just find the difference between them, and then we divide by the accurate answer. And then that's the proportion, and so we multiply by 100%. That gives me the percent error. So our percent error using these equations for, metals and stuff that don't strain very much is going to be 0.006%. You know what I mean? So just very accurate and cool. All right, so hell yeah, I thought this video was going to be way shorter. And okay, so we still got 2 more parts. And what we want to do is we want to find the change in this angle. And I think because I didn't write the strain equation. And do we need the strain equation? No, we still just need this, so we should go back to this. Because I started down the road of radians times radius is arc length. And so if I have a change in length in this direction, this diagonal is going to go from there to there. Cool. And there's no difference between this rotated up here and then just this bottom length is what we're analyzing. And this bottom length, if that changes, the top length changes. You know what I mean? And so in this direction, when we're talking about the strain in this x prime direction. All right, so, and when we're talking about, I guess when, we're going to do 2 things with this, though. For this problem, we don't have any rotation. We don't have any initial shear stress in the xy plane. We just have this going on, and then this going on, which I'm just showing as a positive strain in the y, and I'm showing the positive strain in the x. Even though our input is going to be a negative value. You know what I mean? So that's a pretty good way to do it. Okay, so when this changes in length in that direction, this diagonal is now right there. This angle changed. And that angle change, radians times radius, that's alpha times dx, is going to be this change in length, but it's only going to be this component. This is going to be the arc length right there. That's going to be this hypotenuse sine theta. So this is theta, and so we're going to have ex dx cosine theta. That's that hypotenuse, and we have the sine theta component. Sweet. And we can just say we know alpha, we just drop out the dx. And we're going to have 2 components. If we had shear, we're going to have 3 components due to, so that's where the superposition. We just took this imaginary box and put the normal strain in the x. Then we're going to put that normal strain in the y. This diagonal is going to go up to there. Oh, and then we're going to say this is going to be a negative. We're going to use right-hand rule for the change in angle. And now I get that, because if we wanted to analyze over here, which we will do today, we're just going to say that, hey, this is theta, but I want to know the change in angle of this line right there. And is that what we want to do? Probably, maybe. Yes and no, so we'll get back to that in a second. I don't know what we want to do. I think we want to just do it geometrically, like we're doing. So hell yeah, so that's going to be a negative angle change. This one's going to be a positive. Here's our hypotenuse. This is the arc length, so here's our angle alpha 2. And booyah. So radians times radius. alpha 2 times the radius of dx is equal to this arc length. That arc length is that hypotenuse, which is strain in the y times the initial length in the y, dx sine theta. And then we're just going to have the component, the cosine component. So we have cosine theta. Hell yeah. And that's going to be a positive. So now our change in angle of theta, which in this problem is going to be phi, is going to be, so that change in angle is going to be just alpha 1 plus alpha 2. So hell yeah, let's write it. So we're going to negative strain in the x, cosine theta, sine theta. Same thing here. If this is the angle, the dx's drop out. And the reason the dx's drop out so well is because we have, when we rotated this, we kept this hypotenuse to be dx. And then we made a imaginary box that was dx cosine and dx sine. That is what makes the geometry so simple. Alright, so the change in angle is going to be that alpha 1 and this alpha 2. So plus strain in the y, sine theta, cosine theta. And you can see, hell yeah, if we want to do it, this is just negative strain in the x plus strain in the y, parentheses, cosine theta, sine theta. What they will do is this. So maybe get used to it. They're going to do a negative, oh, bummer. They're going to do a negative strain in the x minus strain in the y. So they're going to do the parentheses like this, and they're going to do sine theta, cosine theta. So that's going to be the change in the angle. This equation I didn't write down, but we kind of just drove it. And so we got x minus alpha y and sine theta, cosine theta. And multiply by 10 to the 6, and we get that, so we're going to get a decrease in angle. So that meant that this thing is going to go that way. And we can do a double check on reality on this, because we just said that the change in length, do we remember these from we said that this was going to be 16. So that's going to be like 1, 2, 3. And we said this change in length was just going to be 500. So if this is about 16, I'm kind of doing like 500, 500, 500, about 16. And then this is going to be drop down 500. So this thing's going to change this direction and then this direction. And so this initial line was right there, and now that initial line is right there. That is an important thing that I would do. And that's why this 600 value and this 500 value, kind of good to have them like this. Now this is sure times 10 to the negative 6, and this is times 10 to the negative 6. So obviously this is 1, 2, 3, 5, and this is 1, 2, 1, 6. You know what I mean? And then we got 1, 2, 3, 4, 5, 6. Hell yeah. And then we got 1, 2, 3, 4, 5, 6. You know what I mean? To pick up those numbers. But hell yeah. I mean, just doing that 16 and 500, it was really easy to see. And now we can see that this decreased. And, yep. Cool. And even though the radian decrease is 128 times 10 to the negative 6 radians, I can't do it right now, but I want to graphically show that. Because we showed that if I had a 1 meter chunk of steel, hell yeah, that 1 meter chunk could lengthen 2 millimeters. Or it could shear 4 millimeters. And so I kind of want to graphically show that. You know what I mean? Show this change in angle, representative. But I didn't show this shear appropriately because, like we had this to be 8, and the change in length was 1/1000th of that. So yeah, I think that's just really difficult to show. Those are just kind of small values. All right, hell yeah. So, all right, so we found the change in length of that side using this diagram. So I'm glad I did this diagram before I started this problem. And now we're going to find this change in angle. But actually, we're just going to kind of end this video because we can do that just from a very simple perspective. Because we know that, check this out, look at this. This thing didn't change angle. So look at this. This didn't change. This is still a 90. Okay. So we knew this initial angle. We knew that initial angle theta or phi is what we're calling it. And we just found out the change in phi. Okay. And so like this is still 90. You know what I mean? This shape is still a full rectangle. If we had some shear, hell yeah, you know, we might, we'd have to account for some difference. But because this is the new angle, this is going to be phi plus this change in phi, and this change is going to be a negative value. This is just going to be that initial angle minus the change in phi. And so this is a minus value, so this angle increases. That seemed like a very complicated way to look at that, where if I know that phi changes by that 128 times 10 to the negative 6 radians, and I know that its initial angle was, so we should write this, 26.56 degrees, where there's 360 degrees in 2 pi radians. So if we do that, divide by 360 times 2 times pi, this is going to be 0.463647 radians. And we're going to go 3 zeros. 1, 2, 3 zeros, 128. So that's what we're going to subtract, minus 0.000128. And we're going to get 0.463519. You know, just numbers that are meaningless. But I think you get it. You had an angle here. It's going to be that much in radians. It decreased. This angle in radians has to be... like this is pi radian. This is pi divided by 2. So I'm going to have, yeah, so this is always, yeah, so I'm bad at the, but anyway, pi divided by 2 equals, what we just did was decrease. So we had phi plus change in phi, and this was a negative. And then we're going to have plus that angle. And our initial setup was pi divided by 2, that's 90 degrees, was phi plus that angle. And so the final angle is still pi divided by 2. So if I have this and I have that and I added phi, I must have to subtract phi. I'm just trying to show you just a bunch of different ways of why this decreases. And then obviously this just increases the same amount. And I think I can just draw it one more time. If this is the initial setup, this goes this direction and then this direction. This diagonal line is now to there. This angle reduced to there. And then so this angle, this angle was there and now it reduced to there. This angle was here and now increased to there. So that kind of shows it. So yeah, one angle was there and decreased. This angle was here and increased. And there, one is decreasing by a change in phi, and then that one's increasing by that same change in phi. Because this final shape, this 90 degree remained. Cool. So when you do have an angle change, you'll have to take that into consideration as well. But hell yeah, so I think we just took the most basic problem and at least we explored it enough where it, we kind of see a little bit of the ins and outs. And for this problem, our initial strain, there was just no strain in this XY plane. This one you can just do from straight geometry. Oh yeah, so that is where we should finish. Alright, hell yeah. So, we have the initial angle as 26.56 degrees. We know that this shape is going to be over here now. And so I can do my new inverse tangent. And let's see if we can do this all in one go. So the new angle, this new angle right here, I'm just going to call it phi final. And this will be phi naught. Phi final will be inverse tangent of this height, which, if we know what we're doing now, is going to be 4 times 1 plus the strain in the y direction. Hell yeah. And that's it. That's just that height. And now we're going to divide it by this length. This total length is 8 times 1 plus the strain in the x direction. Booyah. So this equation is a pretty good one to get the hang of. Hell yeah. So that's our new angle. So I'm going to store it as alpha, alpha w. And so we have alpha w minus alpha theta. We have a reduction. This is how many degrees? 0.007 degrees. And so we need to convert that to radians. If we have a circle, and let's go over this, because I swear it doesn't get... What is a radian? Well, you have a circle. You have a radius. You're going to cut a string that length and drape it, and it's going to get to about there. The angle that forms, that angle is 1 radian. And so this arc length is, so if my radius is 1 meter, r is 1 meter, I cut that string and I drape it 1 meter around the circle. Isn't my arc length 1 meter? Hell yeah. And then my angle is 1 radian. So all of those things are the same. What do we know about a circle? A circle literally only has like 2 components, 3 if you're including the diameter. A circle has a radius and a circumference. And so the circumference is going to be 2 pi r. And that's the arc length. That's the arc length of a 1 full circle. So if I say my arc length of a full circle is 2 pi r, my radius is still like 1 meter. And that means this arc length is going to be 2 pi meters. Cool. And then what's the angle? Well, the angle is... we just said that this angle is going to equal the arc length. So I think yeah, this is tripping me out. Like, I swear I'm going to do this a million times if I have to. But the 1 full circle is just the arc length of a full circle. It's kind of useful to be like, okay, I get that. That's arc length. Well, hell yeah, that's just big arc length. If I go all the way around here, that angle is that angle. We still haven't defined it yet, but the arc length is 2 pi meters. If this is 1 meter, if the radius is 1 meter, the arc length is 2 pi meters. But this is the relationship of radians, radius, and arc length. If the radius is I need to back up, because the radius always stays the same, but so I even got it almost wrong. Whatever the arc length is the angle in radians. So if I had an equation that said, here's arc length, here's radians. These things are two different things. One is an angle, one is a distance in meters. So, all right, hell yeah, ran out of juice, and I was gonna destroy this. Arc length is, yeah, holy hell. So if I have a radius and I chop it and I go to there, that's going to be 1 radian. And 1 radian is, because this arc length could be 1 meter, it could be 10 meters. You know what I mean? So 1 radian is proportional to an arc length of, so if this is the angle 1 radian, then the arc length is going to be 1 radian, that's dimensionless, times radius. And that is the holy reason that I just, have the axiom that radians are bizarre as, and so radians times radius is arc length. When you take radians and multiply it by a radius, you get something normal. So radians times radius is arc length. And you can do this with omega. Radians per second times radius is tangential velocity. Angular acceleration, radians per second times radius is something normal. That's a tangential acceleration. So those are the three that you can use. The radians times radius is something normal approach. So that means that the arc length is radians times the radius. Hell yeah. So yeah, the arc length is going to be, the arc length of a full circle has to be 2 pi r. And so, so that's going to be this side of the equation. You're going to have 2 pi r is going to be the angle for one full circle. Angle of a full circle times the radius. Alright, so obviously this was a pretty hashed up, but this is almost the best that I've done. It's kind of interesting when you always think things are like mysterious. You know what I mean? Just because I have to see it to believe it. I have to start from something that I know is going to be concrete every time, and that's going to be starting with a circle, having a radius, cutting a string, draping it to there, calling that 1 radian, and then just kind of seeing what plays out. And so hell yeah. So the arc length of a full circle is the circumference. That's 2 pi r. And we're saying that arc length is radians times radius. Radians times radius. I know the radius of my circle is r. Well, I'm really interested in the angle of this full circle in radians. And that's what this is giving me. So I can just cancel out the r's on both sides. And so the angle of a full circle, you know what I mean? Don't call it 360 degrees because we're in radians, you know what I mean? But hell yeah, it's just the angle of a full circle. Keep it at that. Is 2 pi radians. And so there you go. So all that just to show that there's 2 pi radians in a circle. Half circle will be pi radians to there. Quarter circle will be pi over 2 radians. I almost forgot why we even did that. So we had this angle in degrees. And so now we have a conversion factor. We have 1 revolution, 1 full circle is equal to angle of 2 pi radians. You know what I mean? You can even flesh this out and say, hey, 360 degrees is equal to 2 pi radians. And then anytime you get an equivalence, I seldomly like to write equivalents like that because they're going to be used in factor label, so you're going to have either 360 degrees divided by 2 pi radians. But now this is a full circle. This is a full circle. Cool. And so this is the equivalent of 1. And you can also write it like 2 pi radians divided by 360 degrees. Alright, and keep writing it like this if it's your first rodeo. By the time you have this on lockdown, then start writing this as, well, I can just divide by 2. You know, I mean, I can factor out a 2, you know, and so I can have 180 degrees is pi radians. Or I can have pi radians is 180 degrees. So that'll be my conversion factor. So right here I'm going to have 180 degrees is pi radians. And so, booyah. So I'm going to divide by 180. Well, let's just do what we're doing. We're going to multiply by pi. So multiply by pi, divide by 180. And hell yeah. And so this gives us the change in angle. And the reason we did this is because this is the most accurate change in angle. Because we used geometry to show that inverse tangent, you know what I mean, was that length final. That length final was the length initial times 1 plus the strain. So anytime that you're going in one direction and using the numbers, and then see if you can kind of, you know, also say what you did. And so we got that length. We got the length final in the x, length final in the y. Squared them, added them, square rooted them. That's going to be this Oh, no. Holy hell. We were just trying to find the change in angle. So that's going to be the inverse tangent of this opposite length divided by this length. And so we just kind of showed you what these length finals in the y was going to be, basically that equation. And so this angle multiplied by 10 to the 6, this is going to be negative 127.98. And so I'm going to store that as alpha, let's do alpha v. Alpha, yeah, where was the other value? I don't even know if I stored it. But the change in angle, yeah, it was, yeah, that's a good one to review. Just because this change in angle, this change in alpha, you know, it's kind of a tricky thing. This moves there, and then so I just want the arc length, and so I'm in this alpha 1 dx, hypotenuse, and sine, you know what I mean? So we have, and that's going to be a negative, so we have negative, that strain times sine theta. Alpha 2 is positive, strain in the y. You know, so that's our first term. Alpha was positive, strain in the y. You know, that length in the y, sine, which is that length, says the hypotenuse. And then we want to find the arc length. That's going to be the cosine component. And so, hell yeah. So you have those two terms. We can drop out the dx. Well, let's redo this one. So we have negative x for our strain, cosine theta, and then sine theta, plus strain in the y, sine theta, cosine theta. Yeah, especially if you can do something and then 5 minutes later you're just like, where did that equation come from? But hell yeah, so this was, and it was very accurate to, it was going to be negative 128 times 10 to the negative 6. And we got a value, so I'm going to store that as alpha u. We got a value, so truly that angle is negative 127.9832. So we do have an error. So this is an approximate. This equation is an approximation. Now this alpha is, you know, it is changing. What's changing? Oh yeah, so on this, if I did have this rotated element, hell yeah, this line does change. And it reduces that way. So this line is now there. And then this line up here, I think, goes this direction. Don't quote me on that. But then I think we don't have any strain. Or no, do we pick up? That'd be interesting. I don't know. I'll have to analyze that later. But I guess for this problem, all we were interested in is the change in this line. We found it, and we know that the final shape is still a rectangle. Where when we rotate this element, you know what I mean? Hey, it's no longer all we did was just look at this rectangle. And so this is an unrotated element. Its diagonal could be considered part of a rotated element at that. But just at face value, this is a rectangle that changed in length this way and then changed in length that way. It had no angle of rotation. This element, it had a diagonal, which could be thought of as an element that, was, if I took this and rotated it up, it would be just like that. And then so I could find, the change in this. So this would probably go that way and maybe go that way. Who knows? I'll have to I'm going to do that when I turn off the camera. But yeah, even these first problems, they're, it's just like, well, how do you use the equations? Well, they're just asking for, hey, this is going to lengthen this way and shorten that way. How does this angle change? You know what I mean? So it's only going to be, and if I did rotate this up, and I found the strain in the x1, y1 plane, this is x prime, y prime, that strain is going to give me this angle change and this angle change together. And basically it's going to give me this reduction of angle. It used to be 90, and now it's either reduced or it's going to be, and the reduced angle is associated with positive shear strain. And if the angle widens, that's associated with negative shear strain. Hell yeah. And these problems, are the introductory to kind of learning about the full equation. And, with the Mohr circle, you have this x1, y1 divided by 2, and this, strain in that x prime. Now this x prime direction can be rotated 360. So I can just rotate it an extra 90 to get the strain in that direction. And so I could rotate it none and get the strain in the x. Cool. And then I could rotate it 90 and get the strain in the y. Cool. And when I do that, I'm going to be able to plot. Typically I'll have a strain in the x, a strain in the y, and then an associated xy, and then negative xy divided by 2. So those are the locations of these points. The center of the circle is here, and now here's Mohr's circle. And then so here's going to be the max. So this is going to be shear strain xy divided by 2 max. And this is going to be the principal strain, and then this is going to be the principal strain number 2, principal strain number 1. Cool. So if at an angle of the point had no initial, this was 0. Like these two terms were 0. So what we had was so let's draw that. Our Mohr circle, x1, y1 divided by 2, and this is strain in the x prime direction. We had an initial, we had EX, but associated with 0. And let's draw this, and let's just say we had a generic one, and an EY, but then we had 0 shear strain. Because this point would be EX, and then my initial shear, and this point would be EY, and then negative my initial shear. So that's kind of how you do that. And then here's the circle. Because the circle now goes through those points, we can know that the max x1 y1 divided by 2 max is just going to be the difference, this minus that divided by 2. So it's just going to be that length is going to be that max shear. So we can find max shear. But that means that hell yeah, this is our initial angle. So we can rotate this, and if we rotate it any amount, we're going to get shear. So This angle went this way, and we're going to get negative shear, and so this angle must be. The only place that we get zero shear is when this angle is 0, or when you flip it and it's 180. So our little element is right there. We could rotate it up to there. We could also rotate it all the way down to there. So we're just keep on rotating that element. When it's in this location or 180, there is the shear strain in the x1, y1. That value divided by 2, or just that value, is 0. But in every other orientation, so that kind of shows that, hell yeah, and all we did was just find the change in angle of this one diagonal. And that wasn't even the full equation. The full equation for x1, y prime divided by 2 is finding the total angle changes of both sides. One is associated with an angle change alpha, and then over here is an angle change beta. The textbooks will always say that angle is going to be positive with the right-hand rule, and so, but we know that they have to couple together. If this angle goes this way and that angle goes that way, that's going to be associated with positive shear. If they broaden out, that's negative shear. And so the textbooks, they have to say this is positive alpha, cool, for positive shear, but this is going to be positive beta, and we have to subtract it. So if I have a negative beta, hell yeah, that's going to be associated. Both of those are going to help make positive shear. If I have a negative alpha and a positive beta, well, hell yeah, this is going to be negative alpha. How does that work out? So our angle change, well, yep. Yeah, if I have a negative alpha, that's going to be increase. This angle from 90 got bigger. And but that alpha angle is negative. Yeah, so your shear strain is alpha, and if that's a negative, you're going to get a negative value. If this is a negative number, that just means that this, went to, that angle increased, and that's going to be your diamond shape. All right, holy hell, this might just be more for me just to kind of piece it together. But hell, that was good, because it was just like I just didn't want to leave. We found the angle change on the diagonal, and I just wanted to know if I did rotate this element, would there be a very similar angle change? And I'm sure there would. It's probably equally proportional. I guess it doesn't have to be. And if I look at the equation, I would see what it's proportional to. And yeah, it's proportional to the strain. You know what I mean? I kind of have that equation from memory. x1, y1 divided by 2 is going to be negative 2ex sine theta cosine theta plus 2 strain in the y sine theta cosine theta. Now we can say that if this is my initial thing and I do that, then or yeah, maybe we can grab a sheet. Yeah, let's try this out. So here's this. We have a rotated element, and it looks like that. I'm going to box this in. If I have positive, and all I'm getting is the shear term. So this shear term is going to go like that. That's going to be a horizontal this way. I'm more interested in the this is going to be a cosine component, so we have ex cosine. Oh, just a second. Oh, no, yeah, this is going to be that initial angle, and then we got to do times the radius. So we have dx sine theta. Remember how this was dx? This is going to be dx sine theta. Hell yeah, so we have dx sine theta. Radians times radius is arc length. Just for this is just radians times radius is this, this change, and that we're going to call that the hypotenuse. and then we're going to take the sine component. So we're going to have, so the angle, so the alpha that's going to form right here is going to be a negative for this. So we're going to have negative alpha 3 radians times radius is this arc length. This arc length is going to be that hypotenuse, which was this radians times radius. So that's that initial gamma xy dx sine theta, and I'm going to have the sine component. The dx's cancel, and now this is my change. So there you go. So this, we pick up a negative, and I just move the negative sign to over there. Hell yeah. And so we have negative sine squared theta. Doing a similar thing over here, and I'll try to go as fast as possible. So we got theta. This is a dy, so this term is going to be dy cosine theta. I'm going to have a shear that's going to pick up that angle. Radius is dy cosine, so that hypotenuse right there is gamma xy dy cosine theta. And now we're analyzing just this side, and if it goes that direction, the angle decreased. And if this is the hypotenuse, that's going to be the angle form, and that's going to be beta. See, the triangles get real small. This is my arc length, and so this is going to be dy. So we got beta dy. This is going to be a negative though, because it's going to be a negative angle, and that's going to be associated with this hypotenuse cosine. And so hell yeah, this is going to be xy dy cosine theta squared. So we're going to take that percent, which is in the cosine direction of that change. Hell yeah. So that's, and then that angle change is going to be negative xy cosine squared theta. That's going to be a negative. That beta is going to be negative. But if I have a negative rotation is associated with positive shear. And so, yeah, I hate that. You know what I mean? Really, we should just be saying, hey, that's going to be a positive value. You know what I mean? So look, it's making this positive shear. That's kind of what we're interested in. You do you on how you figure that out. You got to go alpha minus your betas. And I'm okay with that, because, you know, if you throw it into a computer, you know, you're only going to be able to use sines and cosines going in one direction. So that's kind of why that proof pulls out like that, alpha minus beta. And we can see that this beta is associated with positive shear. So let's just give it a positive value, and we'll give it a positive value there. So hell yeah. So there you go. So this was the shear. And I don't even know why I'm doing this, but I just wanted to know if I did rotate this element up to that angle, I want to know what the full shear is. Is it just going to be double this? You know, that's what I want to know. I want to know if this decreased and then this angle increased the same amount. So let's do it. Because, that's what I thought, because this value is 0 and this value is 0. So by definition it is, you know what I mean? It's going to be that same. Like we already calculated the same thing. So this moved this way by 128 times 10 to the negative 6. And this moves this way in the negative direction. You know what I mean? So we're going to get, this answer is going to be negative. You could associate it with an increase in angle, but both these angles widening are associated with negative shear strain. So let's do this one. It's the same thing we did on the other one, but we got negative 2x sine theta cosine theta plus 2 alpha y sine theta cosine theta. And that's it. And, wait, why do we have something different? Alpha theta, mode and degrees, negative 2x, sine cosine, negative 2x Sine, cosine. Oh, my bad. So this equation, this equation gives the total shears. So yeah, this kind of, I think the tricky thing is, one, like this divide by 2. That'll destroy you. Because right here, I don't have the divide by 2. What I'm doing is I'm finding the total shear for everything. And so that's why we get this value of 2.56 multiplied by 10 to the 6, and then half it, and then we get that 128. So that's gonna drive me crazy the entire time, is that shear is always going to be graphed on Mohr circle as half, but the equation, the preliminary equation, will always be the full value. Or you do you whenever you want to divide by 2 on that. So, all right, hell yeah. Again, this last part was kind of just for me, but it's good to kind of ask questions and see if you can get there. And this proofy part, just this geometry, just to be able to kind of kick this out and see those arc lengths, see those radiuses, see those change in angles, and know that change in angles, negative shear, positive shear, and you have to assess both lengths, and there's no rhyme or reason that either of these legs have to be the same change in angle. It just happens to be the case they were. Primarily, probably, and algebraically, just because we had no initial shear stress. I mean, so if we go back to literally the equation that we just solved for shear, it still was a function of that initial shear. We just didn't have none. And we did have an angle rotation, so hell yeah, we would have had differences in shear due to that. Yeah. I still don't know, because one was at an angle of, if we did rotate this up 26 degrees, this, yeah. Oh, that's funny. Yeah, the one thing in here is like, yeah, if you just wanted to know the rotation of one part of this rotated element, that's a question that I have. Can one of these be different than the other? I'm sure from the algebra, yeah, you would think it would be. But these are the same. The strain in the x cause the equal amount in both. The strain in the y causes equal amount in the both. That's why this came out. So now the question is, does this initial shear strain have a... Yeah, I don't think that is similar, but I don't have the mind to figure that out right now. But it's kind of a rabbit hole that I could go down. So cool. So I think we're done with 7.71, the easiest one that you could do. But yeah, we just kind of figured, I think it's easy and hard at the same time, because you still just you drove like all these complex equations, and then you're just like, how much of those equations are we using? Obviously that initial shear in the xy plane is 0, so that simplifies your equations. And we solved it from geometry. We saw that there wasn't too much error. And that's about it. Alright, so hell yeah. And we kind of went over the Mohr circle. That is always kind of good to go over, for sure. Because that answered my question that, yes, if we do rotate this, hell yeah, that's literally the definition of this diagonal. That diagonal changed, so a rotated element would change. And so I'm glad I did that. And then there's just other things from the Mohr circle, that the max shear is just going to be the difference between those. So even like right now, I could figure out the max shear, and because I just drove the equations, doing these problems really helps you solidify those hellish shortcuts where you're just like, yeah, what is the max shear? Well, it's just taking x minus y divided by 2 times 10 to the 6, and then the max shear is going to be 160 for this problem. So, booyah. And we had a shear of 128, which was substantial. The max shear is going to be 160. times 10 to the negative 6. Alright, I gotta be done. Thanks for joining me. And that's a video.